Indeed, the perceptron algorithm can be seen as a stochastic gradient descent. Remember that a sample is misclassified if yi, w tilde, xi tilde is negative. Thus, a possible loss for this problem can be the sum of all the previous quantities when they are negative. This is exactly the definition of L given here, up to a minus sign, which ensures that the loss is positive. Then, if we consider a stochastic gradient descent, at each iteration, we sample one observation from the dataset and compute the loss corresponding to this sample. The gradient of such term is exactly minus yi times xi tilde, which gives the updating equation below, if we set the learning rate of the stochastic gradient descent to 1. Therefore, we have a nice interpretation of the perceptron algorithm as a stochastic gradient descent procedure. Now that the perceptron algorithm is one of the first iterative methods used to solve a problem involving a dataset. The question we may ask for any learning algorithm is, does this algorithm converge, and if it does, what is its rate of convergence? To answer this question, let's define some notations. Let's take R as the maximum of the norms of xi, W tilde star as the optimal hyperplane of optimal margin, gamma defined as the minimum over all samples of yi, W tilde star, xi tilde, with the constraint that the norm of W tilde star is equal to 1. We have the following theorem, which states that the number of updates needed for the perceptron to converge plus 1 is upper bounded by 1 plus R squared divided by gamma squared. The conditions are quite stringent, since you assume that the data set is linearly separable, which means that gamma is strictly larger than 0. Of course, in practice, it is really unlikely to find a dataset which is linearly separable. When you see such results, the first thing to do is to understand the dependency of the upper bound in the parameters. In this case, if R is large, then the number k of iteration is large, which is consistent, because if R is large, then it means that the dataset is widely spread. Besides, if gamma is small, then the number of iteration is large, and again, this seems logical because gamma is the margin of the hyperplane. If gamma is small, the two classes are difficult to separate, and that the algorithm takes more steps to converge. In summary, we have seen that the perceptron is a model, a neuron, and an algorithm to learn the weights and the bias of such neuron. To this aim, you need to have a dataset. Once the weights and the bias have been learned, the decision function is simply an indicator function of the linear combination given by the weights and the bias. This decision function is linear and thus really simple. One strong limitation of the perceptron is that it converges only when the data are linearly separable. In particular, if the data are not linearly separable, you know that the perceptron algorithm does not converge. Since in practice you cannot be sure that the data are linearly separable, you must never use the perceptron algorithm. It is quite amusing to see now what people thought about the perceptron at the time it was created. The Perceptron project was led by Rosenblatt and was funded by the US Office of Naval Research. Here is a quote of a press conference at the time in 1958. The Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Later, Perceptron will be able to recognize people and call out their names and instantly translate speech in one language to speech and writing in another language. As you can see, people at this time got really enthusiastic about what the perceptron will be able to do in the next years, whereas people knew at this time that the perceptron is only able to work with linearly separable data. If you want to know more about the perceptron, here is a reference you can look at. With the creation of the perceptron, some people, namely Minsky and Papert in 1969, exhibit the fact that it was difficult for perceptron to do some particular things, as detecting parity, the number of activated pixels in a black and white image, detecting connectedness, whether or not the activated pixels in an image are connected to each other, and representing simple nonlinear functions like the XOR function. All that put together creates what is called the first AI winter, which ranges from the early 70s to the early 80s. This term describes a period during which the funds for AI diminished drastically. Here is a quote about the perceptron algorithm. There is no reason to suppose that any of the virtues of the perceptron carry over to the many layered version. Nevertheless, we consider it to be an important research problem to elucidate or reject our intuitive judgment that the extension is sterile. Perhaps some powerful convergence theorem will be discovered, or some profound reason for the failure to produce an interesting learning theorem for the multi-layered machine will be found. This is a quote from the book Perceptrons, written by Minsky and Papert in 1969. This book is one of the starting points of the first AI winter. The controversy between Rosenblatt, who created the perceptron algorithm, and Minsky and Papert is rather famous in AI history. This controversy is representative of two trends in AI, connectionism and symbolic AI.